All so much for coming to this year's Energy Week Lightning Talks. For anyone who doesn't know me, my name is Dr. Michelle Hutchings. I'm the Managing Director of the Vagelos Integrated Program in Energy Research, or VIPER, here at Penn. And this event is really a joint collaboration between VIPER, as well as the Vagelos Institute for Energy Science and Technology, and the Kleinman Center for Energy Policy. The talks that you're going to hear about today really are across the board: energy science, technology, and policy. Our speakers are finalists who are selected from a wide range of different applications from across the university. And they are going to give 8-minute student presentations on their research. And then what we'll do after that is we will then take 2 or 3 questions. We'll kind of prioritize some questions from the judges and then open it up to the audience. But even though we're only taking 2 or 3 questions now, we will have time at the end for questions from all of the audience members to ask to any of the speakers while the judges are deliberating. So we will be able to award 2 awards during this. At the end of the presentations, we'll have a Judge's Choice Award selected by the judges, as well as an Audience Choice Award. And both of those award winners will get an additional $200 cash prize. I also want to take this time to introduce our judges as well. So we have with us Professor Dan Mendiola, who's a professor in the Department of Chemistry. We have Lauren Anderson, who is the Director of Programs at Perry Worldhouse. And we have Professor Alexandra Vojtovic, and she's a professor in the Department of Chemical and Biomolecular Engineering and the Director of the Penn Institute for Computational Science. All right, and so does anyone have any questions before we get started? Cool. All right, then it is my pleasure to welcome our first speaker. So here we have Peter Bazianos. He's a 3rd-year undergraduate student in the VIPER program. He's pursuing dual degrees in physics and astronomy, as well as material science and engineering. And he's also pursuing an accelerated master's in nanotechnology. So welcome, Peter.
Thank you very much, Dr. Hutchings, for the introduction. Hello, everyone. I'm excited to tell you today about atomic scale materials innovation for energy storage. So, in the goal to increase use of renewable energy, it's becoming increasingly apparent that we're going to need to rely on energy storage technology. First, solar, wind, and other renewable energy sources are intermittent, meaning we need energy storage to balance out our supply of energy and make sure consumers can have it when they want it. Also, to electrify our current economy and use renewable energy instead of fossil fuels, like in cars, for example, we need to have new innovative energy storage solutions in those realms as well. So I want to zoom in on the energy storage problem and look at different length scales of how we can innovate our energy storage technology and kind of what kind of computational techniques we have at each level of this length scale. So first we look at a battery pack, per se, in an electric car. We look a little further, we can see individual lithium-ion batteries. We can start to look at material selection, the thermodynamics, what's happening in current voltage, and model those kind of parameters. We look a little further, we can use numerical methods to model lithium-ion diffusion, per se, in batteries. But now if we look a little further, we can see molecular level. And now we're looking at individual lithium atoms and how they're moving at real non-zero temperatures, interacting with materials in the batteries. And if we look even further, we get to the length scale I'm talking about, which is atomic scale. We use very rigorous methods to find electronic structure properties of these materials. And what's really exciting is this goes hand in hand with our experimental characterization abilities and our chemical methods. And we have, with electron microscopy, methods to see at the atomic level as well. So we can directly compare what our computational results are saying and then what our experimental results are saying, and then use that to make better energy storage technology. So it's really exciting. And for a quick overview of what this kind of is and what kind of simulations we're doing, one common simulation method or calculations at the atomic level is density functional theory. So the goal is to find the ground state electron density of the structure we're looking at, but we can't solve the many-body Schrodinger equation with that many electrons. It's just not possible. So what we do is we break it down into a combination of single electron wave functions. So we kind of solve a Schrodinger-like equation, but we use a modified potential to account for those electron-electron interactions and effects like correlation. So one of the coolest projects I've worked on for the past 2 years is developing enhanced cathode materials for lithium carbon dioxide batteries. You may not have heard of it. It's very similar to a regular lithium-ion battery, but now we have interactions and reactions with carbon dioxide at the cathode. And this kind of is really interesting because it provides insight not only into open air batteries in general, but also carbon fixation technology, which is also really up and coming in climate tech. So it's really cool science to study, let alone just the specific application. And if you look specifically at the catalyst we're using, we can see the electronic structure there. It's graphene with transition metal and nitrogen, moieties in there. And we look and we see reactions happen on this catalyst, interactions with lithium and the carbon dioxide that are coming in. And we can see different steps of our reaction mechanism, like a discharge and charge reaction mechanism. And we can even add things like ligands and other additives to the cathode environment to see how we can change what other papers presented, which is iron and nitrogen moieties. How can we change that? How can we make a better cathode material? And from our first results, we found that by getting an entire reaction mechanism, we found that if we just change the dopant from iron, which other papers used, to a different transition metal, we found that the potential determining step was lowered significantly. So already there, we have a super exciting result. It's like, okay, experimentalists, here's how we can make a better battery. Maybe we want to try this out in an experiment. Awesome result. But this isn't what's most exciting about this kind of field. It's the fact that we can look deeper. And we can look at the actual physics and chemistry of what's happening here to determine what's happening and how we can extrapolate to new materials, new catalysts, and new energy storage solutions. So let's look at that transition metal. We look specifically at even individual orbitals on these atoms to see what kind of properties are contributing to these enhanced effects of titanium per se. So we look at the density of states, like the electronic structure, where these energy levels are, and we can find antibonding and bonding orbitals that these dopants are forming with the adsorbates. And we find that the electronic structure with titanium specifically, it has a really high D-band energy center in the orbitals relevant to the bonding. And that actually results in a really favorable absorption dynamic that iron simply didn't have. And that's explaining why, on a deeper level, this is a better catalyst and why we're finding these better enhanced results. And we can extrapolate that to new findings. Also, we did different tests like electron density difference maps to see the effect of something like ionic liquid. So right there's a little cation near the surface, and you can kind of see electrons leaving some orbitals, entering others from this Coulombic attraction. And then we can see why this ionic liquid is providing enhanced absorption. So it's really cool we see at this atomic level what's happening, how we can extrapolate, and then finding new materials we can test for next and use an experiment as well. Super exciting work. The other project we worked on last year, we published last year as well, is on bipolar membranes for aqueous batteries. So this is a new energy storage option. But in this bipolar membrane, it can work in two bias modes. So in reverse bias, it's used to split water, and that's for the production of like green hydrogen, which can be used as an energy storage methodology, splitting from water. And then in the forward bias, like in a fuel cell, the hydrogen and oxygen recombine into water, which gives us our energy. And the bipolar membrane is really cool because it allows each side of the fuel cell to operate at its own pH, which enhances the voltage and overall increases our output, which is really exciting. Anyway, what's really exciting about this study that we did was it used experimental results. You can see NMR we used to define, to see which active sites were on the graphene oxide catalyst, and also computational simulations at multiple length scales. So we had not just the DFT, which is what I worked on specifically, and my mentor worked on the molecular dynamics of it. But I'll play this little video here. You can see that on the right, we also use a larger scale molecular dynamics, saw that motion, and we can see exactly how water is dissociating on this catalyst. It's pretty awesome. We can look at that specific level. And from these results, we were able to find which exact active sites on graphene oxide were really best for enhancing this water dissociation. And then from the DFT results we have down here, we can see the effects of the electric field. So why was an electric field we were finding having so much better results, like enhancing the water dissociation? And we found when we looked at the electron accumulation, depletion, and looked at those interactions at the atomic level, we found what was happening. So it was really exciting to have these results, and we published last year. And future developments in this field are on both the computational and the experimental side. So computationally, the RAP group specifically has been working on, the group that I'm in, has been working on different methods for electronic structure, and really exciting results are ones that combine stochastic, larger scale Monte Carlo type simulations with the first principles knowledge of DFT. So now we're getting that enhanced accuracy, but also larger time scales and quicker simulations. And artificial intelligence is already being used as a really important tool in this field to find out material properties and how they relate to things that engineers are looking for, and also enhance our force field calculations to make them more like the accuracy of things like DFT. And experimentally, we're getting better and better characterization and synthesis methods to see at the atomic level. This semester, I'm interning for a startup at Penn called Hydropore that works on production of clean hydrogen. It's really cool to see that side of things as well. That's all I have. Thank you so much for your time. Oh yes, sorry. Any questions?
So we'll take 1 or 2 questions from the judges table and then 1 or 2 questions from the audience.
Thank you for the exciting talk. Could you maybe tell us a little bit about this design principle that you talked about? Is this transferable to other reactions? I mean, you talked about different chemistries. Can you elaborate a bit more? Because it's a very exciting field, of course.
Certainly, yes. Once we have an understanding of some sort of reaction mechanism or a few reaction mechanisms we might want to test, we can really extrapolate this to any battery chemistry. And then once we have an idea of what kind of might be happening, different steps to the reaction mechanism, we look and can model with DFT to see, okay, here's one step of the reaction mechanism, and we'll model and see, optimize the electronic structure and the energy there. And then look at the next step and the next one. So molecular dynamics, honestly, or something a little larger scale is great for identifying reaction mechanisms themselves. But so once we have that kind of insight or experimental insight for that, then we go into the DFT. So DFT is kind of once we have that understanding, because we can't do those finite temperature analysis at higher temperature. So it's really exciting that we can extrapolate that to any sort of reaction mechanism or any sort of battery chemistry as well, for sure. And I know your research is in that, so you know so much more than I do, of course.
So what, if any, considerations are given to the availability, the impacts of mining on some of the metals that you may want to be experimenting with for use in the batteries? For instance, you talked about the transition from iron to titanium. Does that factor into your considerations or your experiments at all?
Exactly, and I'm glad you asked that, because that's why it's so exciting that we can extrapolate using these chemical and physical insights, because right now we haven't really done such a comprehensive analysis of titanium. But if that's not something that's sustainable and something we can use and for a long-term solution, we want to find other things that have those same properties but are more sustainable. So that's why it's exciting that we can find this extrapolation. So we're not just looking at, okay, every single one we test, but rather what are sustainable options that fall in that category.
Then 1 or 2 questions from the audience. Does anyone have any questions? We have a microphone here.
So if you go back to your first slide that showed the cars and the buildings, as lay people who do not understand some of the complexities of your presentation, if you go back to that first slide on the left, how does that benefit the homeowners and the person that owns that red car?
Yeah, so for energy storage specifically, in the grid scale, it's going to be extremely difficult to rely on clean energy without energy storage. Because right now, the solutions that we have, like wind and solar, only produce during the day. So energy storage makes it so that homeowner right there can have energy when the sun's not shining and the wind's not blowing. Because otherwise, without the energy storage, that would just be a lack of energy on the grid. So exactly, the energy storage makes sure that when you want to flip on the lights, you can, because you have the energy stored from when the sun was shining earlier in the day or the wind was blowing earlier in the day. And you can charge your car when you want to as well.
All right, thank you so much, Peter.
Thank you.
All right. So next we have Alina Ho. She's a 4th-year undergraduate student studying, pursuing her bachelor's and master's in systems science and engineering, as well as economics. So welcome, Alina.
Thank you. So now, more than ever, it's undeniable that we're living in a climate crisis. As the world has begun to understand the consequences, we're also facing the continual consequences of being too slow to act. Cutting emissions and the clean energy transition alone are not enough. To reach net zero emissions by 2050, the US must scale and deploy carbon dioxide removal technologies, known as CDR, to capture and store over 50 billion tons of CO2 per year by 2050, and cumulatively sequestered anywhere from 350 to 1,000 gigatons of CO2. For reference, total global emissions are around 40 gigatons of CO2 per year. CDR is no longer a last resort, far-off technology. Today, it is a critical part of our climate solution. Now, the industrial deployment of CDR requires significant investment in and the development of nationwide transport infrastructure to deliver CO2 to reliable storage. To meet the increase in demand for transport capacity, existing infrastructure is projected to expand over 100 times in capacity. We're going to have to build 1,300 miles of new CO2 pipelines by 2050. Pipeline has been the predominant transport method because of its ability to move significant volumes of CO2 at a low cost. Simply put, it's cheap. On paper, everything pencils out. But the reality is it's nearly impossible to build a CO2 pipeline today in the United States. The opposition has resulted in countless pipeline delays and cancellations. And because these pipelines have failed, the CDR projects that rely on them have failed too. The industry can't gain traction because it can't get transport. We need to seriously consider the alternatives to pipeline, and today I'll make the case for rail, not only as an alternative, but as a primary solution. And before I move forward, I'd like to take a moment to thank my co-authors and advisors for this paper, Pete Sars and Elaine Plorge, as well as the Clean Energy Conversions Lab. And you can find the full publication that inspired this talk at the QR code up in that corner. Okay. So Class 1 carriers, which you can see mapped here. I don't know why the laser is not working. What? Okay. So Class 1 carriers, which you can see mapped here, represent the largest railroads in the United States. They're the primary rail corridors. And we found that for decades, the rail industry has already been safely transporting CO2. As reported by the Bureau of Transportation Statistics in 2017, about 1.2 million tons of CO2 per year are moved safely by rail. And by far, compared to the alternatives like trucking and pipeline, rail boasts the lowest incident rates. Now, we can see that rail transport serves a small but established markets for CO2 offtake, but what are the actual questions we need to answer to scale this transportation method? First, there needs to be a growing market for CO2 supply and offtake, which I hope I've already answered by my introduction. Two, there needs to be a compelling business case for the movement of CO2 by rail, which I hope to make to you today. And three, the capacity of our railroads needs to be enough where we can move significant volumes of CO2. So let's start off. Is there a business case to be made for rail? Pipeline dominates the conversation because, again, it's the most economical option for significant volumes of CO2. However, through techno-economic analysis and cost modeling, we've found that for under 2 million tons of CO2 per year, rail can be cost competitive, if not cost optimal. So let me reiterate this. Rail is potentially more cost effective than trucking or pipeline when moving small volumes of CO2 over small to medium distances. But this type of modeling doesn't even factor in additional costs. The key advantage of using rail is that you're utilizing existing infrastructure. You don't have to build a pipeline, so you don't have to run the gauntlet of permitting and regulation. You don't have to build a railroad because they're already there. In densely populated areas and industrial regions, we can use rail. Now, one of the primary goals of CDR technology is to address industrial emissions in hard-to-abate sectors like cement, steel, natural gas. This translates to smaller projects that will dominate what the deployment of carbon management technologies look like in the next 10 years, not till 2050. And 94% of all these small facilities are within a 1-mile range of a railroad. And rail, more than pipeline, fits the transport demands of these facilities. Most of the modeling done today for carbon transport uses big trunk pipelines that move massive volumes of CO2. And quite frankly, we don't need that quite yet. By overlaying Class 1 railroad routes with CO2 storage locations, we can see there's significant overlap in regions like the Central Plains, the Midwest Corridor, and the Gulf Coast. Now, we find that rail has an opportunity to serve this nascent industry and be complementary to railroads up till 2050. So the last question is, do we have space on our railroads? Fortunately, and also unfortunately, we do. The decline and closure of coal production plants has resulted and has been accelerated by the 2022 Inflation Reduction Act, and it threatens economic collapse in these coal communities. These regions, notably the Northern Appalachian region, lacking alternative industries, which is right up here and right here, have seen massive layoffs and service cuts as coal production dwindles. Now, by repurposing liberated and existing rail infrastructure used to currently transport 70% of the nation's 400 million tons of coal used by rail each year, the carbon management industry offers a potential lifeline for these coal communities. Our estimates suggest that transporting CO2 by rail could estimate around 100 million tons of CO2 per year, but more importantly, it could translate to creating, or better put, salvaging directly and indirectly 60,000 jobs in these communities. Now, I want to highlight a particular region, which is the Midwest Ethanol Corridor, and we mentioned this a little bit earlier. This corridor, spanning the Indiana-Illinois region, is densely populated with ethanol plants near prime geologic storage locations. And these are connected by small railroads that deliver feed directly to the facilities. This means that on-site carbon capture can just directly connect to these rail transport systems. And so you don't have to wait for a big pipeline to be built and then a smaller pipeline to connect the facility to that big pipeline. And we've calculated that these smaller CO2 emitters would only need 4 to 6 tank cars a day to move their CO2. Now, in the same region, a $5.5 billion carbon dioxide pipeline project spanning 5,000 miles over 5 states was canceled at the end of 2023. And this is not a unique incident. All 3 of the region's proposed pipelines were canceled. I've shown you today that 1, carbon dioxide removal technologies are necessary. 2, in the United States, we believe that rail isn't just an alternative. In some regions, it's the only solution. And 3, we have the capacity to do it. So let's not face the consequences of being too slow to act anymore, or else we might just have to find another planet. Thank you.
One or two questions from the judges' table. Dan?
Very nice, thank you. I have a very general question about the transportation using the rail system. Despite the United States having, at least from my point of view, having one of the most, over time, one of the most engaged railway systems in the world, it's still behind most developed countries compared to, let's say, Europe or even parts of South America. Do you think infrastructure is going to be first before we can even consider the transportation of CO2? Because it seems to me like there's a lot to catch up with in terms of the rail system first before we can begin to look into how can we use it towards CO2 transportation.
Yeah, I think that's a great question. But one thing I would know with the United States is that a lot of this existing rail infrastructure is already in use. What we're looking at is that it doesn't need upgrades. The maintenance has already been happening. I think a lot of European countries use their rail system more for public transport, which is why it might seem more developed. But for commercial use, we already have that infrastructure there. And the truth is, it's freeing up as coal production dwindles. So we see a lot of opportunities for that to be repurposed with minimal, minimal trouble in the transition.
And my second question is more chemical based. CO2, as you certainly might know, you can solidify at minus 78 degrees Celsius. Is that just not economically viable to transport solid CO2 instead of the gaseous, which I'm assuming you're looking at a gas?
Yeah, it's better to transport it as liquefied CO2, and that's the way it's transported in the United States today.
So this is liquefied
CO2. And there are actually specific tank cars built for this, DOT 107s, that are meant to transport these hazardous materials. They're known as kind of like the battle cars of all tank cars because they're very well built and safe. Thank you. for your questions.
Thank you for the presentation. And I love that you're talking about avoiding a stranded asset in the energy transition. Do you think this approach could be replicated outside the United States? What do you think some of the cost considerations or feasibility would be if it's successful here?
Yeah, I think this could definitely be replicated across the United States. Actually, in our research in Europe, they're already investigating this question. That's why we started looking at, is the US a good candidate for this? And this actually began at my time at the DOE, Office of Fossil Energy and Carbon Management, where we asked, we don't really know what CO2 is being moved on rail, but we want to know if we can use it for this purpose. So it's definitely already happening in Europe, and we think it can be replicated anywhere.
Now, one or two questions from the audience. Maybe has a microphone for you. Oh, great.
Thank you for such an eye-opening talk. You made points about rail and points about the pipelines. You said one of the pipelines was closing, or maybe many of them were canceled. Do you think they're being canceled because rail is seeming to be a viable option and they're choosing one over the other, or are the cancellations independent of the viability of rail?
Yeah, that's a great question. So right now, the cancellations are just independent of alternatives. They're happening because there's such strong opposition and safety concerns to building out new pipelines in the United States. The reason why for my talk today is that in most of the literature and the conversations around CO2 transport, we don't see much of rail being discussed. So, thank you.
Thank you, Lena.
Thank you.
All right, our next speaker is Christopher Johnson. He's a fourth-year PhD student in chemical and biomolecular engineering. So welcome, Christopher.
Thank you so much for the introduction. Thank you all for coming, and I am very excited to show you guys the research that I've been doing for about the last year regarding charge transport. And I'd like to start us all with a bit of a question. What do massive stacks of distillation columns, desalination plants, and fuel cells for energy generation all have in common? They've all got a component of separation in them. You have an input that has a mix of materials, and you want your output to be a different mixture of materials or one material only. The separations are a massive part of our chemical industry, and by some estimates, they take up to 15% of our industrial energy expenditure. But there is a way that we can reduce our energy expenditure and improve the lifetime and performance of these materials, and that's by using membranes. You can selectively allow some materials to pass through a semi-permeable layer to get over to one side and cut energy usage by up to 90%. There are some problems with membranes that we use for a lot of charge transport today. We have effectively gotten some good quality results, but there exist problems in how we think about the physics and their usage. Generally, these films are dense and disordered, where channels form when they swell with water. It's a bit of an inconsistent picture of ion motion, and the scientific consensus is a little muddy. They're also perfluorosulfonic, the top performers, and if that doesn't scare you immediately when I say that, just know that they're not very great for the environment or human health on the whole. So we've come up with an alternative, and that is by using a surfactant aqueous channel, a surfactant that we've designed to chemically link together, think of it like a fancy soap, and forms a little clear plasticish film that on the inside has these aqueous channels that are about 1 nanometer in size. We know the dimensions, and we can control for these dimensions to allow species to move through. Additionally, these aqueous channels can also form really fun shapes that are interesting to look at for the science and the physics behind motion in confined spaces. These could be anything from these hexagonally packed honeycomb-like cylinders to this mathematically beautiful shape called a gyroid. Now we ask the question, what can we learn about the ion physics in confined spaces, and how can we improve processes by using order in membranes to separate materials? I have had the great fortune to be part of a seed group funded by the Vagelos Institute. Some of the researchers that I've been working with for the past year are here on the slide, and we've been asking these questions. Because when I say ion motion, what we probably all think of is the high school picture of what an ion means, like a hard sphere bouncing around spaces. But we kind of like to think of it more like the play places that you would see at old fast food restaurants. It's a complex system. There's, like, in this example, there are ideal sizes of humans that will move through these play spaces. There are areas that they will hang out in. Sometimes the walls are sticky. What we then get from that is a picture that can be applied to ion motion. There exists a balance between materials that will move through as if they are moving through with water, and then there will exist materials that are clinging to the walls, running along. It's a balance, and we want to see if we can use it to solve the engineering problem of separating out complex mixtures of ions. So if you have sodium bromide and sodium chloride, could the bromide and the chloride be separated? So we measure the conductivity of different types of ions in the hexagonal membranes and the activation energy, which is effectively a measure of how hard it is to get that ion moving initially. And what I'd like you to get from these graphs is that there are differences within our materials. You can see an order of magnitude difference between the fastest and the slowest of our membranes, and then there are some that are significantly hampered, very hard to get moving. They are stuck to those walls within the different membranes between the different ions. And the conclusion that we draw from this is that we can hypothesize that the polarizability, how hard it is or how easy it is to move the partial charge to one area of this ion, will allow it to cling to the wall differently and will be either more stuck or less stuck. This can be used to separate complex mixtures of different ions. And, it teaches us a bit about the ion surface interaction. Some of the people I'm working with are looking at these different interactions, and we are investigating how each ion will cling. We also are looking to see how these membranes work in fuel cells. So taking one of the ions that we looked at earlier, hydroxide, a very aggressive kind of ion that you want to move from one end to another within a fuel cell. That would be right here. We found our membranes are remarkably resilient, so we wanted to look at how the differences in the shapes, those cylinders and those gyroids, will impact the performance of our membranes. So the cylinders have smaller pores, but a smaller solid volume present, while the gyroids are a bit more tortuous, but are larger. They use their space better. What we look at is a measure of hydration, a lambda value that is effectively the number of waters per charge center present. And we find that the rules driving our ordered membranes are very similar to disordered membranes. So we see here on this graph that we swell our membranes, and they respond by increasing conductivity in kind. But there's a caveat. At higher temperatures, we do begin to see a difference between the types of order. The gyroid port per charge is much better at moving ions than the hexagonal membrane. This is a good design consideration, because if you have a membrane that can occupy a larger space with a gyroid, you'll want to use that, but you have to consider how hydrated it's going to end up being. These hexagonal membranes will eventually be more hydrated than the gyroid and will have a better performance. So when you are developing these membranes, you want to think about where does the gyroid appear, how hydrated can it be, where does the cylinder appear, how hydrated can that be? And this design consideration, we hope, can be applied to other types of surfactant systems, as ours is chemically specific, but it's a general enough recommendation that you can make it. So in conclusion, what we have done over the last little bit is created membranes with highly specific nanoscale order, explored how all these membranes have dissimilar ions clinging to their polar spaces when they're confined in these nanoscale spaces, and shown how you can design these membranes for either complex ion separations or use in fuel cells. Thank you very much, and I hope to answer some questions for you.
One or two questions from the judges' table? Alex?
Thank you. I'm a bit curious about some of the length scales that you presented here, because some of the ions that are transported through these will, of course, travel short or longer distances, depending on the conditions. Could you elaborate a little bit on that in these two classes of structures that you had?
Yeah, so the two different structures, they both exist in the 1 nanometer-ish scale, so that limiting dimension of transport is approximately a nanometer in both cases. They both have In the cylinder's case, there are two dimensions of around 1.5 and then around 0.8 nanometers. In the gyroid, it is almost consistently 1.5 nanometers. So they exist around that same space.
Yeah, I'm more interested in like how far can the ion go through them?
Oh.
Like, so if you look at the figure at the top, that middle membrane layer, of course, has a dimension. How does that correspond to your pores, basically pore lengths, not widths?
Yeah, okay. So what we have done in our experiments is we have worked with membranes that are anywhere from 10 to 200 microns in thickness, so transport along that dimension. You also can transport a couple of centimeters in either direction. That's what our experiments have been limited to. It's just instruments, yeah.
All right, any questions from the audience?
So you do mostly anion transport. Would this be possible with cations? Like, do you have any, like, I guess, intuition on how this might be transferable, if that makes sense?
That is a wonderful question. So there's two directions I can go with that. The first is that we do believe that switching the charge, you could investigate similar ideas. We are chemically limited by the fact that the surfactants we use have a positive charge. But there is an idea that you could use a positively charged membrane to do very complex separations with positively charged materials. They're not going to want to go through, but if you have a large enough space, there will be some materials that get through. Separating, say, lithium and sodium is a really big problem. Can we do that with these kinds of membranes? That's another future work that we're hoping to look at with these materials.
Thank you so much, Christopher.
Thank you.
All right, and next we have Arwen Kozak. She's a second-year master's student in environmental studies.
Hi. Thank you all for coming. I am a second-year Master's Environmental Studies student. I'm also a research assistant at the Kleinman Center, and that's what I'd like to talk to you a little bit about today. So, in particular, a lot of my research at the Kleinman Center has focused on carbon offsets. We know we need to reach net zero or beyond, and we know we need a lot of tools to do that. We can avoid emissions, we can not let them happen, we can remove emissions that have already occurred, and kind of broadly speaking, we can do that industrially, so using manufactured technology, or we can do that using nature-based solutions, so better managing existing ecosystems or natural resources. Some sectors can transition more easily than others, but even sectors that can transition easily, there are time constraints. We've already heard about some of those today and the need for developing them. Some industries are harder to decarbonize, and setting aside a kind of deindustrialization argument, which could be its own presentation, assuming we want to allow them to continue to emit, industries like heavy transport or cement, we want to give them a little bit more time to decarbonize, we need to figure out some more creative paths to net zero. We've talked a little bit already today about direct air capture and what that can look like, and while that is a very exciting and promising solution, it operates on a different timescale. Right now, 27 direct air capture plants globally capture about 0.1 megatons annually. Scientists estimate that by 2050 that could be 10 gigatons a year, but right now we're at 0.0001% of that. So we need to buy ourselves a little bit more time. Today I want to talk about one way we can start to do that, which is a nature-based solution, which is avoided deforestation. This is a solution that can supplement, though not replace, these technologically important investments, which we've heard about many of them today. So on the surface, it feels like a really good idea. We should not be cutting down trees. We know that. In the 2015 Paris Agreement, they talked about carbon markets and carbon offsets, which is this idea that if we want to represent reduced emissions by a certain target, we can buy and trade and sell those to allow different places that are at different developmental stages to still reach net zero. right? But allowing us to sequester and store carbon for longer periods of times has a lot of complications with it. Research that originally started as how we could price carbon has run into a lot of barriers as we've tried to figure out what exactly is happening in these international carbon markets. We can ask questions like, who is really benefiting from these? Are we really being respectful and engaging with communities that are offering up these deforestation projects? Are we actually representing additional reductions? If I pay to protect a forest that is already officially or unofficially protected, that doesn't really represent an additional emission, so I shouldn't maybe be able to count it towards my company's net zero calculations. Are we really stopping these emissions, or are we just displacing them? Are we not cutting down trees in this acre and cutting down trees in the acre next door, or even an acre across the world? Are we just displacing those emissions? How can we verify what's going on? We cannot be everywhere at once, and a lot of these projects are talking about really huge swaths of land that we don't have direct access to. Even with GIS and satellite technology, it's really hard to know exactly what is happening. Are we greenlighting further emissions for corporations? Are we saying, don't worry about decarbonizing your sector because you can pay for deforestation somewhere else. Keep emitting as you were. And nature is, by nature, impermanent. It is at ever-increasing risk of natural disaster and man-made disaster. So this is a reason for pause, right? These are a lot of reasons that mean that natural-based carbon offsets and deforestation are criticized. But there are reasons that these should be legitimized as a way to truly reduce carbon. They can lead to, if done correctly, community development and community engagement. Carbon sequestered is better than carbon not sequestered, right? We don't want to walk a line of saying, we don't need to worry about deforestation, we can't really quantify it, so go ahead and chop down whatever trees you want. We want to keep that carbon sequestered. Protecting nature and stopping deforestation also increases biodiversity, which has a host of co-benefits that could be its own presentation. But there are a couple sticking points. Companies are using this as a greenwashing tool. They are saying that we are avoiding deforestation elsewhere, so we are meeting net zero, or we're on track. But when these offsets are not properly verified or not properly regulated, or when they are not super accurate, we are allowing companies to either continue emitting as much as they have been, or even emit more than they were before. And we cannot say for sure how long these carbon credits, so to speak, are going to be sequestered or stored for, because we don't know when a wildfire will come. We cannot know for sure that they're not going to get burnt or cut down, or another natural disaster will befall them. So this kind of begs the question, what's the point of talking about them if there are so many issues and we haven't been able to solve them? Like I mentioned, in 2015, this was a part of the Paris Agreement, and as of December, it is still not operational because the debates about how to make this work, how to make an international carbon offset market work, are so tricky and so hard to navigate for reasons like the ones I just talked about. Deforestation is just one example of many. But we know that something has to change with the way we manage our forests and the way we manage our other nature-based resources. We know that immediate action can delay and can reduce the worst harm caused by climate change. We know that it can deliver co-benefits. We understand what it is to have a park or a forest available to us and what it is to not have that. Delayed action will lock in high emissions infrastructure, it will increase stranded assets, it will escalate costs, and it will increase losses and damages. We know this. Nature-based solutions are not comprehensive. They are not a one-size-fits-all that is going to get us to net zero with no other work. But although my research has yielded more questions than answered, I think it's important to think about them. How can we have legitimate, equitable, and trustworthy accounting on a global scale? Maybe we can't. How can we protect nature in its own right versus stopping corporations from using it as a greenwashing tool? Maybe we cannot, but we have to try to figure it out. We are not in a place to rule out an entire class of solutions because we don't know how to do it perfectly. It is worth investing time in figuring out how to legitimize these carbon offsets, especially the nature-based ones, to buy us time for some of the amazing technology that we've heard about to catch up and help us stem the worst harms of climate change. We do not have time to waste. Thank you.
Questions from the judges table?
You know, there are a lot of climate impacts to be considered, and I'm wondering if you, what you think, where you think NBS, nature-based solutions, could have the biggest impact on stopping the effects of climate change. If you think that would be flooding, perhaps in urban areas, or mental health, because people have access to parks. What do you think their greatest impact would be, even if they can't be accounted for otherwise?
Yeah, I think where my research is starting to focus at Kleinman is on kind of those mental health human scale benefits. You know, more locally speaking, how can we use this to encourage local investment because it just makes people happier. But I think on a broader scale, flooding is definitely a part of it, and also the way that, because these credits are being bought and then that money is going to communities that perhaps wasn't getting them before, that can be used for other mitigation efforts. So that's not a direct benefit of having it. I think the best benefit is the human scale benefit. But increased funding to these communities that doesn't rely on deforestation can help fund other mitigation efforts.
Questions from the audience? Yes,
Thanks. That was a wonderful talk. Avoided deforestation, really popular solution, I think, for the noted co-benefits, but also because it's very cheap. Yet maybe 90+% of those have been shown to be overcredited. So how do we fix this? And do you see a role in policy to help?
I don't know how we fix it. I do see a role in policy. I think like there's a reason that it's still being discussed at places like COP28 and how we can have an international market that is verified accurately and how we can do all of this. I think we are reaching a point kind of in the timeline of this where that's no longer going to be where the primary time should be invested. I'm hesitant to say like we shouldn't try to have an international carbon offset market, because I think that we should, but I think that trying to focus on ways you can encourage corporations to do it for other reasons that maybe don't depend so much on like this accurate accounting for carbon, like can we get Comcast and Xfinity to invest in local offsets in Philadelphia because it makes them more popular with the people that they're selling to, even if they can't say for sure this is going to be X number of carbon credits for my net zero plan.
Yes, thank you so much for that presentation. It reminded me of a movie I just saw recently called Trees and Other Entanglements. Have you seen that?
I'm not.
It's a film by Irene Taylor, I think that's her name. Very fascinating film. And the reason why I bring up the film is because in the film, they show about a corporation that actually reforests. So it's not just deforestation, but reforestation. And I'm wondering what you think of that concept, you know, in terms of them cutting down the trees. Because as you know, corporations are there to make profit. Right. And if you let them run amok, they'll cut down everything. But somehow, some of their CEOs or leaders are coming up with this concept of replanting the forest or reforestation. And I'm wondering what your take on that is.
Yeah, that's a great question. It's definitely like another case study that we've looked at that for the sake of time I didn't talk about today, but reforestation is a really interesting kind of nature-based solution. On the one hand, like people probably here know a lot more about carbon sequestration and the chemistry of it than I do, but from what we synergy of saying we're planting all these trees, they're sequestering carbon for a certain period, and then they're still kind of going back to this economic development because they're able to deforest and reforest again. And there's still some carbon accounting that can be done to see that it's still net zero if they're sequestering more in those early days. So it's definitely a good tool.
Thank you, Erwin. All right, next we have Colby Snyder. So Colby is a second-year undergraduate student in the Viper program. He's pursuing dual degrees in physics and astronomy, as well as chemical and biomolecular engineering. So welcome, Colby.
Hi, I'm Colby Snyder, and I study material science solutions to extreme urban heat in the Composto Lab. So I'm sure you all know that global temperatures are rising, but what might not be immediately apparent is that densely populated areas around the world are already experiencing elevated temperatures because of the urban heat island effect, which causes cities to get much hotter than their surrounding regions. With buildings that absorb heat and retain it overnight, few trees to provide shade, and dark surfaces that absorb energy from the sun, these cities are going to see extreme climate impacts sooner than we might expect. One of these places is the city of Chicago. All the way back in July of 1995, a high pressure zone approached the city and caused temperatures to reach 106 degrees Fahrenheit. And thanks to these weather factors and the urban factors I just described, residents had no way to escape the heat. After just 3 days, 739 people had died, mostly the elderly and those who couldn't afford to turn on their air conditioning. Unfortunately, Chicago is just one example of this, and since then, heat waves have continued to increase in frequency as well as intensity and duration. And with the UN projecting 68% of the global population to live in cities by 2050, this could be devastating. Fortunately, addressing heat is well within our technological reach, and my work in the Composto Lab aims to integrate engineering research with community outreach to address these problems as quickly as possible. Today, I want to tell you a bit about each of these approaches and how I believe together they provide a framework for solving more energy challenges. So, we started this work by looking at several promising heat mitigation strategies, like replacing asphalt, planting trees, and covering dark surfaces with materials that stay cooler. This last approach, specifically cool roof coatings, is especially promising because they're easy to install and can directly reduce costs for electricity through air conditioning. There's two main strategies of doing this right now. Radiative cooling, which works by reflecting the majority of incoming sunlight and then beaming infrared heat energy back into outer space, and evaporative cooling, which works by absorbing moisture overnight in absorbent polymers or other materials, and then releasing it during the daytime for a sweating-like effect. And in the past couple years, researchers have gotten really good at making materials with both of these approaches, known as super cool roofs, which just means they get even colder than the surrounding air, even under direct sunlight. And that's super exciting, but they were developed in different parts of the world, and there aren't many fair comparisons of their performance in real settings. So with this in mind, we wanted to address that problem by designing our own apparatus to do fair comparisons of high performance promising materials. And I started by 3D printing these boxes, which simulate the thermal environment inside of a house. And then I programmed thermometers and a solar intensity meter that let us repeatedly and consistently measure how different coatings influence this internal temperature and the roof temperature itself. So this data is an example of one of our experiments that charted temperature over a 30-minute time interval. And I won't get into all the data for the sake of time right now, but if you look at the orange and the green lines, you'll see something really interesting. So the orange line, which is labeled white roof, is actually just a commercial white paint that you could buy at Home Depot. And then the green line is a porous polymer coating, and you can see that it's almost 18 degrees Fahrenheit colder than the commercial coating. And the way we did this was by using a technique called phase inversion, which lets us introduce micro and nanopores inside the polymer, giving it exceptional radiative cooling ability. And then with that, we had established a framework for fairly comparing materials, addressing the first gap in the literature, and identified a winner. But there's another problem with cool roof coatings, and that is that the super cool materials I just told you about prioritize performance, not practicality. and many of them cost 10 times as much as that commercial white paint, or break apart after just a year from being applied. So if we want these coatings to be truly impactful, we have to focus on more practical factors like durability and cost effectiveness. And for that, we're turning to evaporative cooling. We're investigating a cellulose-based hydrogel that's inexpensive, highly absorbent, and we can tune its durability by adding filler materials, like the dots you see in this picture here. So hopefully this work is going to contribute to a commercially viable product eventually, and that could address the second gap in the literature. But no amount of scientific research is enough to solve these extreme heat issues without first understanding the problems faced by real people in real communities. And that's where community outreach comes in. In the real world, these coatings need to be tested on specific roof types in specific communities to justify investment, and then they need to be delivered to the neighborhoods that need them the most. This map of Philadelphia shows census tracts and their heat vulnerability index, and you can see that neighborhoods in North and West Philadelphia are disproportionately exposed to extreme temperatures. To see why, you can look at these satellite images on the right. The top photo is Hunting Park, one of the most heat vulnerable neighborhoods in the city, and the bottom image is Fairmount, a neighborhood that's relatively safe from heat. If you look closely, you can see that Hunting Park appears a lot darker than Fairmount, and that's actually because of a difference in roof coating materials. There's fewer cool roofs in Hunting Park. And this difference in material selection translates directly into a difference in the heat experience that community members have. On some days, Hunting Park can be 20 degrees Fahrenheit warmer than Fairmount. So a single lab environment can't possibly replicate the diverse challenges faced by different communities across Philadelphia or across the world. And that's why this semester we're exploring partnerships with Philly community organizations so we can let the needs and challenges they've already identified guide our research. As the climate crisis intensifies, we don't have time to continuously pass responsibility back and forth between researchers and community leaders. Instead, these two groups need to work together in parallel to make sure we get climate solutions right the first time. For cool roof coatings, this means listening to the needs identified by communities, like durability and cost efficiency, to inform our research. With these practical roof coating materials, we can reduce energy costs, save lives during heat waves, and buy the world more time to halt climate change. Thank you.
Thank you for the wonderful talk. I just had a very general question about the ways on how heat can be dissipated. When you showed that, I think one of the slides you had like 4 options or 3 options. I was surprised not to see the one where you could actually use the heat to promote work, to get work out of heat, which is something that chemists are familiar in doing, and engineers are also familiar in doing. Why wasn't that mentioned, or do you have an idea of why that would not be under the list of priorities?
Yeah, definitely. And that is super interesting. And one thing that's been discussed a lot, maybe not exactly direct conversion of heat to work, but conversion of heat to electricity through solar photovoltaics is pretty interesting, of course. But for this, when we're trying to reduce urban temperatures at a large scale, it's really important that we get as great coverage as possible, and that means driving costs as low as possible. So something like a paint you buy from Home Depot is going to be like orders of magnitude less expensive than a solar cell or a heat engine on top of your building. So that's why we're primarily exploring this. But yeah, definitely in the future, that would be an interesting direction to explore.
Just wondering if what some of the challenges you anticipate or that you've dealt with in trying to test materials on houses in those communities that are most vulnerable to extreme heat, and how might you overcome them, or how have you overcome an example?
So I think the biggest issue I described broadly as durability, but that really means a lot of things. So specifically adhesion to surfaces, and then how the material withstands environmental conditions like UV radiation. And the first challenge, which is adhesion to surfaces, that's where it's really important to see what roof types exist in different communities, and then either bring samples of them into our lab, or even better, test them outside.
Do people let you just go onto the tops of their houses?
Not yet, and that definitely would, that would be challenging. But it's important that we at least look and see what environments are there so that we can bring it into our lab. And then for things like UV resistance, that's something that we have addressed. And you can use materials that are better suited for these conditions. Like the PVDF polymer I described is UV resistant, so it doesn't really yellow or lose its reflective properties after several years in the sun.
Amazing, thank you.
Any questions from the audience?
I was just curious. So, like you said, Huntington Park and Fairmount Park, Hunting Park and Fairmount had like different, I guess, roof colors. Do you have any idea like about the context behind why they have different roof shadings? I guess like, is it like cost or just it happened to be that way? Like, is one building material more accessible than the other?
Yeah, exactly. So I don't think I have time to go into all the historical factors that have led to this difference in material selection, but I guess posing it as selection is kind of misleading, and Fairmount is a more affluent area than Hunting Park, so it's easier for them to access these newer, cooler materials.
Hey Colby, thanks for the great talk. I was wondering if during your research you had observed any effects or predicted or theorized about the effects of durability of the underlying material, such as preventing warping from reflecting more heat or moisture that might be degrading the underlying material through the evaporative cooling?
Yeah, that's a really good question. And ideally the materials are impermeable so that moisture can't get through and cause things like warping that you described. And we haven't ourselves gotten into those applied studies where we're looking at them, but we are working with a collaborator at the Dow Chemical Company, and they do a lot of those exact studies at their exposure farm. So they're definitely important things to consider.
Awesome, thank you.
All right, thank you, Colby.
Thank you.
All right, and our final speaker is Claire Zhang. So Claire is a second-year undergraduate student in the Viper program. She's studying dual degrees in biology and bioengineering. So welcome, Claire.
Thank you. So like Michelle said, my name is Claire Zhang, and I'm a sophomore in the Viper program. So my current research focus is on nanoparticles. And to get everybody to understand how small we're looking at, I want everybody to imagine the width of a single strand of hair. Now divide that by 1,000,000, and now we're on the nanoscale. So I'm sure you've heard about the power of nanoparticles. They've been used to treat all sorts of cancer. They are cleaning our oceans, and so it should not come as any surprise that they can also help us with renewable energy. So how can nanoparticles help us with lowering energy consumption? Well, they are catalysts, and they can increase reaction rates. So at its most basic form, catalysis is where a molecule enters a system, it attaches to a catalyst, and then usually with the input of heat, it'll exit the system as a new molecule. Now, why do we want to go so small with nanoparticles? Well, as we get smaller, we can increase the surface area to volume ratio of catalysts. So that means there's more surface available for reactions to happen on, while the catalyst is not taking up much space. In addition, for nanoparticles, we can control their properties to match specific reaction conditions for different renewable energy reactions. Now, this is already being used all around us. For example, in fuel cells, nanoparticles are being used all around us in electric vehicles for the catalyst material. In addition, for energy storage, they're being used to make energy density more efficient. In hydrogen production, we can use nanoparticles to create clean hydrogen, which is then used as an alternative fuel source. And lastly, there's a very interesting type of nanoparticle called a quantum dot that has special optical properties and is currently being implemented into solar cells. They're making the conversion of sunlight into energy more efficient and effective. But I wanted to focus on how we can modify nanoparticles themselves. Instead of applying them to a new system, I am focusing on how to change the properties in the element itself. So first, I'm focusing on a magnetic nanoparticle. That means that instead of absorbing external heat in catalysis, the nanoparticle can generate heat by itself. So we can heat nanoparticles selectively by applying a magnetic field around a whole system, and that minimizes energy loss to the surroundings. However, the elements that we use for this, like iron and nickel, are not great catalysts. So that's why we need to use a precious metal shell for the surface chemistry. I've been making nanoparticles like this one that have a magnetic core and a precious metal shell. And that allows us to get high catalytic activity and selectivity, which means we can optimize for the product that we want and minimize any byproducts or unwanted products. So I'm applying this to a system called inductively enhanced catalysis, where we flow an alternating current around a whole system of nanoparticles, and that allows them to generate heat from the inside out. The nanoparticles can then use most of the heat that they generate all by themselves instead of an external heat source. And this is just one example of the results that we've obtained. As you can see, when a magnetic field is applied, we can reach very high rates of conversion in different types of reactions at lower temperatures. So clearly, magnetic nanocrystals can help us save energy and even generate more renewable energy. But they need to be scaled up, and therein lies a big problem. Traditional methods of synthesis for nanoparticles is highly inefficient. Sometimes it takes even more energy to make these particles than they would eventually save in catalysis. So the basic principle behind this is we add metal precursors to a solution, and over time, they'll nucleate into clusters and grow. We can then change the size and shape of the nanoparticles depending on how much time we leave them under heat for, or how high the temperature is for the synthesis. But the traditional method, which is called thermal decomposition, requires us to leave these particles in solution at 300 degrees for 3 or sometimes even 4 or 5 hours. This is highly energy inefficient, and we're looking for new ways to make the synthesis more efficient for higher scaling up of nanoparticles. So one way that has been very underdeveloped that I'm looking into right now is called microwave synthesis. So just like how a microwave would heat our food from the inside out, microwave synthesis for nanoparticles is going to heat individual particles rather than heating the entire external system. So over the past couple of months, I've been able to create the same standard of nanoparticles with very similar properties and similar catalytic activity as traditional synthesis in under 15 minutes. Sometimes these particles can nucleate and grow in just 5 minutes. In addition, with microwave synthesis, we can change the power, the pressure, and the temperature at which we make particles. And that's really great for optimizing nanocrystals to different energy-saving reactions. So as you can see, the red line, which represents microwave synthesis, is able to reach the same exact temperature as traditional heating mantle synthesis at exponentially lower times. Sometimes these reactions can happen in mere seconds. However, this method of synthesis has not been widely developed, and therefore there are a lot of different properties that we need to look at to change and to grow specific types of crystals. The future of energy catalysis is going to rely on both optimizing properties and scaling up. And the nanotechnology that I'm talking to you about right now is a great example of how we can use optimization and scaling to change the future of renewable energy, one nanoparticle at a time. Thank you.
Yeah, very exciting talk. Could you mention just the scale of the synthesis? Because if we want to scale up and use this material in real applications, how much can you make of it?
Yeah, so right now we are working in very small batches. It's not applicable to an entire industry just yet, but the thermal decomposition methods have been favored because you can apply them to much bigger systems. Like for solar cell applications, we're already producing a lot of quantum dots at once. And the problem with thermal decomposition is that even though you can make very large quantities, it's very uneven heating of the particles. So that's why you need to hold them for such a long time, make sure all the particles are reaching the same temperature. So eventually, we will need to integrate both microwave devices that are big enough to handle this and also synthesis methods to optimize for scaling up microwave synthesis.
Thank you for that wonderful talk. Could you go back to the slide where you showed the precious metals that are going to be, yes. Somebody could argue too that since you're trying to save in energy, you're going to the precious metals, but also the refinement and the costs associated with precious metals can go against that. How do you take into consideration that factor?
Yeah, so that's actually something that I've been focusing on because these precious metals, specifically the four I've listed here, which are the best for catalysis, platinum, ruthenium, rhodium, and palladium, they're very expensive. And so what I was trying to do is make this shell as small as possible or as thin as possible, sometimes even just 1 atom thick, so that we can optimize the magnetic behavior inside and the catalytic activity outside, but using minimal precious metal material. So that's something that has also been underdeveloped in research because it's very difficult to make uniform nanoparticles when the shell is so thin. There's many different types of agglomeration or corrosion that can happen. So I'm looking into the best ratio of magnetic core to precious shell that we can use.
Thank you.
Questions from the audience? I have a question there. In the slide, I think a little bit after this, where you're looking at the heating, the microwave and the mantle, what do the pink and black lines represent?
Yeah, so those are different types of radiation that cannot be scaled up to a large extent. I believe one of them is UV radiation, and yeah, I don't remember what the other one is, but these are both very volatile and they just can't be applied to a big system. So something like microwave synthesis is very safe. We can reach really high pressures with it, and it's still able to make really specific nanoparticles, and that's what we want to tune to as many different reactions as we want.
So is the formation, okay, sorry. Thanks, Claire, for the great presentation. Is the formation of the magnetic nanoparticles based on both heat and rate and method of impelling? And if so, how does the microwave synthesis make up for the lack of impeller that the thermal decomposition has? If it, just from the diagram, it looks like it doesn't have an impeller.
Yeah, so the rate of heating is really important, and that's something that is even more tunable on the microwave compared to thermal decomposition. And that's because we can change both the rate of heating and the rate of pressure increase inside the microwave. So we can make really specific properties depending on what settings you can change on the microwave. And that's another great benefit, except it hasn't been shown what different types of pressure can do to the nanoparticle that you're synthesizing.
Yeah, thank you. Such an interesting talk. I guess you are using the magnetic field to heat the nanoparticles so that they'll be more catalytically active. But sometimes catalytic reactions sort of run away and get too hot. Are there any opportunities for magnetic cooling or to keep the temperature at an optimal point that you might want? Or is it only for heating purposes?
Yeah, cooling would be a really interesting area to explore. Right now, what I'm trying to initially find is what that maximum or ideal temperature is in order to make the nanoparticles, and we want to make it as low as possible. So I think once we find out what that maximum is, then it'd be great to try to find a cooling method. The microwave itself can't do that, but if we can increase or change the rate of cooling to make different shapes of particles, which is usually done with thermal decomposition, that would be an interesting opportunity.
Thank you.
Thank you, Claire.
Thank you.
All right, so we've heard from all of our speakers. What we are going to do now is invite the judges to come just exit out of this door so you can talk and come to a consensus for the judge's choice. What we will ask everyone in the audience or anyone live streaming to do next is you all get to vote for your favorite speaker as well. So please either use this QR code, or we do have paper ballots if you if you want one. Just raise your hand and we'll pass them around. Does anyone want a paper ballot? Everyone good? Oh, behind you. All right, so just take some time, vote once for your favorite presentation. Speakers, you are allowed to vote as well if you'd like. Once you are done with that, I'll just give you a few minutes to vote, but then we're going to open it up while the judges are deliberating for Q&A for any of the speakers. So if you have questions for any of the speakers, then we can take those now. And I'll just close this a little bit. Yeah, as long as we have one representative. While people are finishing voting, does anyone have any additional questions that they'd like to ask the speakers? All right, if not, no worries. We'll, when the judges come back, we'll announce the award.
Yeah. Oh, it's always great. Yeah. Yeah, sometimes I get one like over because that's about a mile.
I'm colorblind, so I don't mind. Maybe that's the trade for the green. Oh, really?
Yeah, Oscar was like, I don't know which one, so I'm just gonna go with it.
These are so nice. And how could this like amazing?
Yeah,
I was not expecting like this. Nice one. And this one.
I can't bring, I need to like go meet some microphones to people that are actually microphones. Totally fine, we give them some non-microphones.
Yes, I'm good.
Have some stuff?
Yeah.
We'll see. Don't worry about it. Oh yeah, because it's your ear. Are you busy?
Yeah.
Where you're going next?
Yeah, it's, yeah. I choose one of those sheets. I choose soft things, like on myself, but I know. Yeah.
So yeah, if you will, she's in a tutoring session, I think, from like 5. So I just, yeah.
Yeah.
Yeah, we learned shots. Set up on a tripod. Shot of her, talking and explaining. That's probably all that's needed. There's other students in the common area.
Yeah.
You get some of those shots too, just of them working, chatting. Because we're just trying to show how the floors, like, communities are. Just need a few. You'll see something that's unique or community talks about.
Let's get in touch. Okay.
This one?
All right, so I think we are ready to announce our winners. But first of all, I wanted to say that you all gave such excellent talks. Even if you don't get one of the awards today, I think you should be really proud of the effort that you put into the talks. They were all really amazing. But first, I think, first let's give another round of applause for our speakers. All right, and do the judges want to announce their choice?
Oh, certainly. Okay, I think it was quite unanimous, but we chose Colby Schneider as our winner.
Congratulations, Colby. And then Nadine, do you want to announce the Audience Choice Award?
Yes, and the Audience Choice Award went to
All right, well, thank you everybody for your attention and for attending today's Energy Week Lightning Talks. I want to thank you again to all of the speakers for such amazing presentations. And also want to put a plug in that feel free to grab any food or drinks as you're leaving, but then there's also our Energy Week poster session that is happening starting now, downstairs in the Singh Galleria, just down as you're exiting the building. We're going to be running this poster session from 4 to 6. So thank you all.
Lose, you lose. I love that he wasn't in the room when you're impressed because I distill policy, which pleased and not surprised. All the time. Oh, I'm glad you're glad. Yeah, I'll catch you later.
Yeah, I will just